In this demonstration, I'll show you how to perform linear approximations in calculus. What we're doing is making sure that the values of f at x and L at x at the point x is equal to a match, as do the values of the slope there. L of x is just another function, the tangent line, which can be used to approximate f at x at the x values near a, which is the point at which we found the tangent line. Let's get started with question number 1. Question number 1 asks, find a linearization of f of x, which is sine of x, at a is equal to 0. We'll start off by writing out this formula that was provided. F at a plus the derivative of f at a times x minus a. Let's start off by finding what sine is at a. Sine at a is equal to 0, and you can confirm by using your calculator. And we're going to find that the derivative of sine is equal to cosine x, and now we will substitute that value of 0 into this, and we end up with 1. The last step is to substitute a into our formula along with our findings. I'll highlight this, and I'll highlight this for clarity's sake. L at x is approximately equal to 0 plus 1 times x minus 0. And if you simplify that, you end up with L of x is equal to x. And that is our tangent line. Our tangent line, represented by blue, is L of x. Let's proceed on to question number 2. In this question, they are asking us to find a linearization of f at x is equal to the square root of x at a is equal to 25. Let's start off by finding out what a is equal to 25 is equal to. We end up with 5. And similarly, we will now find the derivative of f of x. And remember, this radical is the same thing as saying x to the power of half, so we can actually use the power rule here quite easily. 1 over 2x. And now we will apply 25. One over 2 times the square root of 25, which is equal to 5. And therefore our answer is 1 over 10. We will use the linearization formula, which is L at x is equal to approximately f at a plus f prime at a x minus a. Let's substitute what we know. We know that f at a is equal to 5 plus 1 over 10, which is 0.10, times x minus 25. So our formula is, for the tangent line at a is equal to 25, 5 plus 0.1 x minus 25. So this formula right here would represent the tangent line at a is equal to 25. In our last example, they're asking us to find a linearization of f at x is equal to 1 over x at a is equal to 2. The first thing that I would do in a situation like this is revert this back into exponential form, because it's easier to work with. This is the same thing as this, mathematically speaking. I'll write down the formula. Lx is approximately f at a, so we'll need to find that, plus f prime at a, and we'll need to find that, times x minus a. So let's begin by finding f at a. 1 over 2. Let's find the derivative of this. The derivative of that is equal to negative 1, x to the power of negative 2. And another way of writing this is saying negative 1 over x to the power of 2. And now we'll apply that a is equal to 2 into here. you end up with negative quarter. Let's apply everything that we just found, this value and this value, into our formula to find out our tangent line. 0.5, which represents half, plus negative 0.25 x minus 2 should give you the tangent line formula. 0.5 minus x minus 2 over 4. And there you have it. 3 examples on how to linearize functions at any given point. If you found this tutorial helpful, please support our channel by subscribing or by liking this video. If you have any further questions, you may visit our website at biology-forums.com. We are an online service for students seeking free homework help. See you soon.